Hello and welcome. This is a practice exam that we've set up for the first unit of our Chemistry 30, just in case it's your first chem exam in a while and you're slightly jittery. You can go through this. This was not written by the same person who did the actual unit exam, but it is pretty close. If you do okay on this one, you should do well on the next. So I'm just going to plow through it and do every single problem, talk my way through it, and try to remind you about the important points you need to know to solve it. I have not rehearsed any of these, so I hope I get through it all on the first try and come away looking brilliant, but you might see me stumble and have to recover a little bit, and that's not so bad to see either because that happens in science. You get started on an approach and realize it's not going to work and have to adjust. So that may happen. You can chuckle at my expense, and I will do my best to give you a clean chemistry experience. Let's see what we can do with this. So there is no question one. Question one on this exam is instructions for how to handle the written part if you're doing this exam online, which we are not. So don't worry if you're seeing this start at question two. And they say honey has a high concentration of fructose. There it is. It has the same formula as glucose, but a different structure. During a combustion reaction, energy is... Okay, so they say all these things about fructose and glucose and honey, none of which end up mattering. The question is just in the abstract, when there is a combustion reaction, if we burn propane or sugar or gasoline or whatever, what happens to energy? Energy is, remember that combustion reactions are generally exothermic, so you get things like propane burns reacting with oxygen, it produces carbon dioxide, water, and because fire is hot, we know these reactions are typically exothermic, they release energy. So energy is released into the surroundings. It's got to be one of these. C and D are out. And then they talk about the products have higher or lower potential energy than the reactants. Well, if it's an exothermic reaction, you know the energy diagram looks like this, where the combustible thing like gasoline or whatever has high potential energy and then loses that energy as it burns. Why? Because that energy is released into the surroundings as heat and light and a little bit of sound. So any exothermic reaction is like this, where you start high and then the energy drops. This is the energy contained in the chemicals. If it were an endothermic reaction, we'd see a step up where the chemical species start out at low energy and then absorb some during the reaction and end up higher. So energy is released into the surroundings, and the products have lower potential energy than the reactants should be that. By the way, if you haven't attempted this exam on your own yet, I encourage you to do so. This should be a much better activity for you if you actually go through it and attempt it, and then go through and see what my thoughts are on the questions. If you're doing this kind of passively and just letting the questions roll over you, I don't think it'll be as good of a prep. Your call, but I would definitely recommend you try the questions for just with what you know already and then follow up with this afterwards. Okay. Magnesium carbonate, that would be this, MgCO3, can be used to produce a white pottery glaze. When glazed pottery is placed in a kiln, high temperatures, blah, 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 into... Okay, so magnesium carbonate decomposes when it's baked in a kiln into magnesium oxide, and carbon dioxide, which is a gas and would just float away. And they say the decomposition of this magnesium carbonate changed the temperature of water by... okay, so there are two energy transfers going on here. First of all, we have water heating up. And they're saying a magnesium reaction, which we'll get to in a minute, releases enough energy to do this. I'm interested in this because this looks like something we can solve for right away. We have a formula that tells us the total energy required to heat something equals its mass times its specific heat times its temperature change, which in this case would be 150 grams of water times the specific heat of water, and the temperature change was 4.57 degrees. So you will now hear me mashing my calculator. 4.19 times 4.57 Okay, what I get from that is 2,872.2. Now, because I did this mass in grams, just grams, this is going to come out in joules. We're not working with kilo units here, so grams and joules. The thing is, when we do our delta H, typically those come out in kilojoules, and indeed all the answers down here are in kilojoules, so I might as well switch to kilojoules while I'm here. Instead of 2,872, I'm just going to say that's 2.8722 kilojoules. I divided it by 1,000 because it takes 1,000 joules to make a kilojoule. Okay, so that's the energy that the water absorbed, and they're saying the decomposition of 2.5 grams of magnesium carbonate was enough to release this much energy. So, what's the molar enthalpy of reaction? We have another formula that says the total energy released by a reaction equals the number of moles of chemical that reacted times its delta H, which is what we call the molar enthalpy of reaction. We want to find this. So, divide both sides by n, and you get the delta H we want to find is the total energy divided by the number of moles. Well, we have the total energy, it's this. This is the energy the reaction produced because it's the amount of energy the water soaked up. So that is 2.8722 kilojoules. And the number of moles is, well, how much magnesium carbonate do we have? Bad news. They didn't give it to us. They said grams instead. Well, that's okay. We're used to finding a number of moles from a mass. Number of moles is mass divided by molar mass. It's 2.5 grams of magnesium carbonate. The molar mass for magnesium carbonate, which is MgCO3, is magnesium's 24.31, carbon's 1201. Oxygens are 16 apiece, and there are 3 of them, so that would be 48. And so, more calculating. 2.5 divided by, I'm using the bracket feature on my calculator. If you don't have that, you'll have to work out your molar mass ahead of time. Plus 48. I get that the number of moles is 0.02965. These answers all have 3 sig digs, so carrying 4 sig digs here should be all right. So we care about that number of moles because up here we're doing delta H equals energy over number of moles. Here's the energy, and our number of moles we now know is 0.02965. So 2.8722 divided by 0.02965. And from that I get the delta H is 96.9 kilojoules per mole. Now, they never said anywhere in here whether the temperature is going up or down, and so I don't really know if this is an endo or an exothermic reaction. Happily, they don't seem to care in the answers. There isn't any reference to these being positive or negative. They're kind of defaulting to positive, but it looks like they primarily care about the number, and there's our 96.9, just like we found, so feel pretty good picking that. All right, so 2 separate stages. As soon as you see a temperature change, you are almost guaranteed to need this. And there was also a chemical reaction, and so in those cases, generally, they produce or they handle the same amount of energy. It's this absorbed the energy that this reaction made. And so you can find the energy from one reaction or from one calculation and then say, okay, you over here, you must have been transferred that same amount of energy because it was produced by one of them and absorbed by the other. Okay, what have we here? Ozone is in equilibrium with oxygen. Okay, so there's a reaction here where ozone, O3, reacts with O, a lone oxygen atom, and if you put in enough energy to get over this hump here, then you can produce two regular oxygen molecules. So this represents ozone being destroyed and converting into regular oxygen. And you may recall that the difference in energy between the beginning and the end here is what we call the delta H for a reaction. So between that level and this one is our delta H. And this extra energy, this bump you have to get over to get the reaction started, is what we call the activation energy. So the reaction will not start unless you can pay this amount of energy so far, usually by providing heat. This is just like you have a rock up here and you want to get it down to here. Before you can get the rock to roll downhill, you must get it over this initial bump. That's what we call our activation energy. So what are they asking us about this? Match the numbers on the diagram with the statements given below. You might use a number more than once. The activation energy, okay, well I gave that one away. That's 1. This bump is the activation energy. Activation energy is how high of a bump do you have to overcome before the reaction will go on its own. In other words, before the rock will start rolling downhill on its own. In this case, that far. The enthalpy change for the forward reaction, that would be our delta H, that's 3. The activation energy for the reverse reaction, okay, so now imagine we're going from right to left. Or imagine that your rock is down here and you want to get it up to this platform. Now, all this is the bump you must overcome before the rock will roll the rest of the way on its own. You have to get it all the way from the bottom here to the top of this peak. That distance they call 2. The activation energy going backwards is quite large. And the enthalpy change is just the distance between the two platforms, so it's 3 again. Delta H is the same number whether you're going forward or backwards, but the activation energy can look very different. It can be a little bump like this, and then it goes the rest of the way on its own. From the other direction, it's a huge bump like this, and then it goes this little bit of distance on its own. So what you'd enter for this is 1, 3, 2, 3, because it's a numeric response. In Neptune's atmosphere, ultraviolet light breaks up molecules of methane as represented by the following reaction. Okay, so CH4 breaks into CH3 and hydrogen, and they give us enthalpies of formation for 2 of those things. In the breakdown of methane, energy is, okay, so they want to know if this is absorbed or released. They want to know if it's endo or exothermic. So we need a delta H for this reaction, and we can find it because Hess's law says the delta H for a reaction is products minus reactants. On our product side, we have CH3, which they tell us has a heat of formation of 145.7. The other product is a single hydrogen atom, and they say those have a heat of formation of 218.0. Minus. And our reactant is methane, which they didn't give us, but it's in our data book. They had to give us these 2 weird things that we don't normally see because they are not listed in the book, I don't believe, but CH4 is methane. And the book tells me its heat of formation is minus 74.6. Don't forget the negative sign. They're important. Okay. If you're thinking this should have been a 0, H2 is 0. That's naturally occurring hydrogen. Individual hydrogen atoms like this are a different thing and not the natural form of hydrogen, and you won't find them in our data book, but thankfully they gave us the number. So there's our products minus, here's our 1 reactant. And if we total all this up, let's see, for products, 145 plus 218 is going to be 363.7. These two negatives cancel, so we get plus 74.6. Add those up, and we get 443, 447, 448.3. Now, they don't care about the number here, and neither do we really, but we do care that it's positive because that tells us this reaction is endothermic. If it's endothermic, that means it consumes heat. You must put in heat to make this reaction go. So energy is absorbed, that means. C and D are out. And they say energy is absorbed as what bonds are broken. Well, we start with CH4 here, which has, this isn't the three-dimensional structure, but close enough. This is what methane looks like, and then one of these hydrogens snaps off. So apparently we're breaking a carbon-hydrogen bond. So energy is absorbed, a carbon-hydrogen bond is broken. A is looking pretty good. Okay, written response. These are the sort where you write your answer on paper and then you scan or fax or do something with that to send your written answer to the instructors so they can mark it and comment it if need be. Cetane, C16H34, is an important ingredient in diesel fuel. Write a balanced chemical reaction for the formation of cetane. Okay, so we must write a reaction that makes cetane. And this is the simplest reaction you can imagine. It's just the one where you take each of the naturally occurring elements that makes up cetane and you write it separately. So we're saying if this is a carbon-hydrogen compound, it's made with carbon and hydrogen. Carbon doesn't have a subscript. When you find carbon, it's typically C, or sometimes they write CN, but the standard formula unit for carbon is just a single carbon. And for hydrogen, that's a diatomic gas, so we write H2. And from those things, we're going to produce cetane. If this is supposed to be a balanced reaction, well, it's certainly not right now. We have one carbon turning into 16 carbons. That's not supposed to happen. So let's get that fixed. Here there are 16 carbons. Here there must be 16 carbons. Easily done. Here there are 34 hydrogen. So here there must be 34 hydrogen. 17 times 2 would make 34. And that's it. That's a balanced chemical reaction. If they had said thermochemical reaction, I would now be finding a delta H and writing plus such and such number of kilojoules on one side of this reaction. But they didn't ask for that. They just want chemicals, so we're done right there. And I'm a little bit lax about this, but let's do this nice just because the reaction is the entire question. Carbon at standard temperature and pressure is a solid. Hydrogen at STP is a gas. And cetane, we are told, is a liquid, which makes sense because it's part of diesel fuel. Okay, a student performed an experiment to study the energy change associated with the dissolving of glycerol in water. So glycerol is a type of alcohol. You put it in water and the water heats up or cools down as this substance dissolves into it. With most chemicals, there's a small temperature change when you mix them with water, but it's usually so slight that you don't notice it. But if you take careful measurements, you can pick it out and you can use it to figure out what the delta H is for that chemical dissolving. The student assumed that the solutions have the same specific heat and density as water. Fine, we do that a lot. The measurements required to determine the enthalpy change for the dissolving of glycerol are... Okay, in this experiment, we've got, again, two energy transfers happening. You would have the glycerol dissolves, which is a chemical reaction. So this is how you would find its energy. The other thing you could measure is, as that happens, the water heats up or cools down. And so you get this amount of energy produced. And these two amounts of energy would be equal. So what that means is in this experiment, these are all the measurements that you'd have to take. You'd need the mass of the water, the specific heat for the water, well, we just know that. the temperature change for the water, and then on the glycerol side, you'd need the number of moles of glycerol, and the delta H for the glycerol is the thing we're trying to find. So that gives us a bit of a checklist. They're saying which measurements above are required to determine the molar enthalpy for glycerol. So if we are trying to find this, what other measurements do we need? Well, this is the mass of water. We need that. Specific heat for water, we don't need to measure that because we haven't memorized it's 4.19. So not on our list. I quickly looked through to see if maybe they'd mention it because they say specific heat of glycerol, but they don't mention the specific heat of water, so we get a pass on that one. Temperature change for the water. Well, they don't mention that explicitly, but how do you find the temperature change for water? Remember, you do T final minus T initial. To find delta T, you actually need two temperatures. You need the temperature of the water before, and then you need the temperature of the water afterwards. And they play with the phrasing a little bit to try to mess with you, but this final temperature of the calorimeter and contents means, well, the water is the main content of the calorimeter, so these are talking about the same thing. You'd need both of those temperatures. And there should be one more thing. Do we need the mass of glycerol? Yeah, we do, because look at this. We need the number of moles of glycerol, but you can't count moles, so what do we do instead? This number of moles we'd find by doing the mass of glycerol divided by the molar mass of glycerol. So yeah, we would need that mass. We wouldn't need the specific heat because the glycerol is not heating up or cooling down, it's dissolving, so 3 is no good. And the final temperature of the glycerol, we don't really care. We care about the temperature of the water because that's where the energy was being absorbed. But 3 and 5 we could do without. Okay, what do we got now? Honey has, okay, we've seen this before. What are they going to do with it now? Honey contains a lot of fructose, which is fruit sugar. Fructose has the same formula as glucose, so they're both C6H12O6, but the way that they're arranged is a little different in glucose and fructose. And they say if we burn some fructose on a calorimeter that contains 250 grams of water and the temperature increases, we've seen this before, haven't we? Two things happening. Water is heating up, and the water is heating up because some chemical reaction occurred. So, yeah, this is a little bit familiar. Can we find the heating up energy here? It should be, we need the mass of water, and they give us that. We need the specific heat for water, and we carry that in our heads. And the temperature change was 3.85. So if we crunch that out, or have an electronic device that will do it for us, times 3.85, we can get an amount of energy, 4,032.875. I'm going to round that to 4,033 joules. Remember, this mass was in plain old grams, so this energy is in plain old joules. But all these answers are in kilojoules, so I'm going to roll my units over, divide this by 1,000, and you get 4.033 kilojoules. That's how much energy this reaction must have released. So, they're asking us for the enthalpy of combustion for fructose. That's our delta H. Delta H would be total energy divided by number of moles. The total energy is 4.033 kilojoules divided by, and now we encounter a trap. Do you see it? How many moles of fructose do we have? Don't say 1.5. See this? This is not a typo. If we just had this, it would be moles. This little m makes it millimoles, 1.5 thousandths of a mole of fructose. So the actual amount that goes down here is 0.0015 moles.
Sneaky, but it does happen fairly often, so you got to watch out for it. So 4.033 kilojoules. 4.033 divided by, and our number of moles is 0.0015. From that, I get that our delta H is 2,689 kilojoules per mole. Now, from these data, most of these have 3 sig digs, or the least sig digs we have in any of these is 3. So this should be cut down to 3 significant digits, which unfortunately is not enough to write 2,689. So we have to go to scientific notation, and that means we get 2.69 times 10 to the 3 kilojoules. The other way you could write that is 2.69 megajoules, but this one is what they expected. And notice that it's negative. Did we know it's negative? In a previous question, they were talking about the temperature just changing. They were being vague about whether it was up or down, and so we didn't know what to say for our delta H. Now they're being explicit in saying the temperature increased, the water got hot. If the water got hot, that means the reaction must have been releasing energy, meaning it's exothermic, meaning the delta H should be a negative number. So yeah, in this case, they have given us enough information that we should say the delta H either has a negative sign, or we should use the word released or something like that to be explicit about which way the energy is flowing. Good habit to get into.